Okay, so this is the first Jamboard of Unit 8 on the energy of reactions. So you can see there's three images at the bottom of this Jamboard, and I just really want to set the table for your homework assignment, which is to read an excerpt from the Napoleon's Buttons book and to watch the three YouTube videos linked to Google Classroom. So let me pull up this image first. Here we go. It's being a little laggy. Okay, this is an image from our previous unit. And so students will look at that and they'll say, gosh, that looks like a image representation of a balanced chemical equation. So what we have there is we have the atoms of a propane molecule and the atoms of 5 oxygen molecules. And those atoms will undergo a chemical reaction, and they'll have a fundamental rearrangement to form 3 carbon dioxide molecules and 4 water molecules. And as we were learning last unit, this is balanced because there are the same numbers and types of atoms on the left-hand side, meaning the reactant side, as there are on the product side. And so, for example, we have 10 oxygen atoms here, and we have 10 oxygen atoms over here. 6 right here in this section, and 4 oxygen atoms here. We could do that for the carbon and for the hydrogen as well. When students are first learning about chemical reactions and balancing chemical reactions, and they learn that it's just a fundamental rearrangement, we can almost imagine ourselves taking these atoms on the left and pulling them apart, much like Legos, and then reassembling them to the right. However, in the next analysis, we need to ask ourselves, well, why is it doing this? There isn't any person to pull those atoms apart on the left and to rearrange them. So what are the driving forces that make a chemical reaction happen? So that's what we're starting to look at in this new unit on energy of reactions. So to that end, you're going to watch 3 videos, and you're going to read a chapter out of a book, the Napoleon's Buttons book on TNT. And so I'm going to reduce this image and start to look at the energy of reactions. And so, although this image is not to be found in any of the videos or in the book, it's really a fundamental chemist's graph to explain the energy changes in a reaction. So as you will learn from the reading in the YouTube videos, there is energy stored in the bonds of the reactants. And I think that makes the most sense when we talk about a fuel. And we say, oh, there's energy stored in the bonds there. So that's why we use fuel, whether it's wood or gasoline or propane. And when we have that chemical reaction of the combustion, we are accessing the energy stored in those bonds. So the idea of energy stored in bonds seems reasonable. And so in this graph on the y-axis, we have that energy stored in bonds, also referred to as chemical potential energy. And then on the x-axis, it's reaction progress. And that really just means that time's going by. So what I've started there with is I've started a line there that's to represent the energy of the reactants. And we're going to let time go by, and then we're going to draw another bar there for the energy of the products. And so this first one, and in the videos and in the book, you'll read the term exothermic reaction. And what that means is that as those atoms rearrange from reactant to product, energy is released. There's actually less energy stored in the products than there were in the reactants. And that's very intuitive because we think of, when people first think about chemical reactions, they think of an explosion, say. So we're accessing the energy stored in those bonds. It's released to the surroundings. We feel that energy as warmth. That's the so-called exothermic reaction, a term that we'll want you to learn. So in terms of this graph, what you would see, I'm just going to grab a pen here. What you would see is you'd start with some arbitrary amount of stored energy in the bonds, and as that exothermic reaction proceeds, you're going to end up with less energy stored in the bonds of the products. And so if you started with a high amount of energy stored in the bonds of the as the atoms are arranged in the reactants, and you have less energy stored in the bonds as those same atoms have now formed their products. That energy was released from the system. It was released to the surroundings. You feel that warmth. That's called an exothermic reaction. That's the one that's most intuitive. Let me shrink that image and then go to the last one. I'm just going to erase that mark there and pull up the final image. Okay, so what you'll be watching in the videos and what you'll be reading in the book, actually I don't think it's in that book excerpt, but you'll also learn about the endothermic reaction. That seems very non-intuitive when we first learn about it. So the classic example that we have there is a cold pack. And so what happens is you have an injury to your arm or your leg, and you want to cool that injury, and so you go to your first aid kit, you grab that instant cold pack, you smash it, and you shake the reactants together, and all of a sudden that cold pack gets cold, and you put it on your arm or your leg or what have you. So if the chemists try to produce this same chemical potential energy reaction progress graph, what they're going to find there is that the reason your skin feels cool is because that reaction is ultimately pulling energy from you. You're starting to feel cold because as that reaction proceeds, it's drawing in heat energy from you. And so the way that affects this graph is that the energy of the stored energy in the products is actually higher than it was in the reactants. So in this classic, more intuitive explosion, we tap into the energy stored in the bonds, and we have less energy stored in the bonds of the products as the reaction progresses from left to right. Here, this less intuitive one is one where there's actually more energy stored in the bonds that are formed in the products than there were in the reactants. And in order to drive this reaction uphill, so to speak, it's drawing in energy from your body, and that's why you're feeling cold. So that's the instant cold pack. The one on the left, the exothermic reaction, is very intuitive for physics students that have watched the cart roll down the hill. Or when you think about the boulder rolling down the hill, it's very intuitive to go from potential energy and decrease the potential energy of the system. It's less intuitive, but chemistry offers that option as well, to have some reactants and their stored energy, and then mix these two reactants together and all of a sudden have the potential energy go uphill, so to speak. So it definitely begs the question, what's the driving force for this? We're not going to answer that today. We just want to recognize that there are indeed these two types of chemical reactions, the so-called exothermic reaction and the so-called endothermic reaction. Again, you'll watch these in the videos, and you'll read particularly about the exothermic reaction in the book excerpt.